Welcome to HRS IT Zone. This is the first in a series of videos on data analytics. In today's video, we're going to be looking at a brief overview of the steps in a data analytics project. We will then be taking a closer look at exploratory data analysis using a Kaggle dataset on student habits and their academic performance. We will be doing this in a Jupyter notebook, and we will also be creating basic graphs to explore the distributions, trends, and relationships that exist in our dataset. The first step in any data analytics project is to define the problem or objective that you're working with. This is the question that you're trying to answer or the problem that you're trying to solve. This is your starting point. Once you've nailed this down, you can move on to the next step, which is where you go out and gather the data that you'll need from whatever sources are relevant. If the data that you need does not already exist, you might want to look at doing some surveys or other alternative methods of data collection. If the data that you need does exist, your life is a whole lot easier, and all you need to do is pull it up from whatever database or spreadsheet it is located in. After you've got your data, you need to explore and understand it. This is when you'd be checking for any missing values, weird outliers, patterns, duplicates, basically anything interesting or anything that doesn't quite look right. Then you want to clean and prepare your data. Think handling those missing values, correcting those errors and inconsistencies that you found during the exploration stage, and so on and so forth. This is one of the most important parts of any data project, because if the data that you're working with isn't clean or consistent, then the results that you derive from this data could end up being unreliable or irrelevant. Take a city column in a dataset, for example. The same city could be listed multiple times, but spelled slightly differently or with different capitalizations. This can really mess with your analysis, so now is when you'd be wanting to fix that sort of thing. Once your data is in good shape, as in it's clean, consistent, and ready to go, you can start digging deeper and analyze your data. Think statistical methods, descriptive statistics, visualizations, building simple models, finding and exploring meaningful relationships, spotting any patterns or trends, maybe even doing a bit of inferential analysis. All of this depends on your project and your objectives. When you've got some solid insights, you'll want to visualize your findings so that they're easy to understand. This is especially true if you're sharing your insights with non-technical stakeholders, which is often the case in many business contexts. Non-technical stakeholders can be anyone. It could be the client you're doing the analysis for. This client may have no background in statistics or analytics. It could be an internal team, perhaps a marketing team, that needs your analysis to make decisions around product advertisement. A non-technical stakeholder is anyone who has no background in statistics or data analytics. A good visual representation of your insights can really help these people make sense of the data and can support better decision making, which at the end of the day is what data analytics is really about. Finally, based on all of your analysis and visuals, you'll want to draw some conclusions that hopefully answer your original question or solve the problem that you started with. This is when you'd be looking at interpreting and communicating your results. So summarize your insights in clear, simple language. This is absolutely key. Create visualizations like charts, graphs, and dashboards, and focus on actionable recommendations and not just the numbers. Most of the time, stakeholders care about the why and not the how. So focus on why your analysis is important and not how you did your analysis. This was a brief overview on what a typical data analytics project looks like. But as an aside, it's always a good idea and highly recommended to document your work. Keep records of your steps, your code, and your findings. Document the decisions you make while cleaning and also during the analysis of your dataset. And when you're creating reports and presentations and dashboards and so on, make sure that the audience is at the center when you're creating these visualizations and these reports and these summaries. And tailor your presentation to your audience and your project needs. Anyway, getting back to today's video. In today's video, we're going to be zooming in on a specific part of this process, namely Exploratory Data Analytics, or EDA for short. EDA touches on several of the steps that I just mentioned. It's all about getting familiar with the data, looking for missing values or inconsistencies, summarizing what's there, and starting to spot patterns and relationships. The insights that you find during your EDA will help shape the rest of your analysis. Like we said before, you can get your data from many different sources, but for the purposes of today's video, I'm going to be using Kaggle. There are loads of datasets on Kaggle that you can use for personal data projects and also for Kaggle competitions. Today, we're going to be looking at this specific dataset on student habits and their academic performance. So this is a simulated dataset that explores how the lifestyle habits of students affect their academic performance. And it has 1,000 synthetic records and over 15 features, including study hours, sleep patterns, social media usage, diet quality, mental health, and so on. So to analyze this dataset and to carry on with our EDA, I'm going to be using Jupyter Notebook. Jupyter Notebook is super useful because you can execute the code, you can display the results, and also add any explanations and charts all in one place. So it's very user-friendly. And it's also really beginner-friendly. But you also have alternative software that you can use, like R, specifically RStudio. You also have Google Colab, which is very similar to Jupyter Notebook, and you can also use VS Code. So before we start, I just wanted to mention a small but crucial piece of information. So when you are working with a specific dataset, you want to make sure that that dataset is in the same folder and directory as your Python notebook. So we're going to be working on the Student Habits Performance CSV file, and it's located in the same folder, which is Data Analysis, and in the same directory as my IPython notebook on EDA. So let's open up our notebook. So before we do any of our EDA, we need to import the packages that we're going to be using for today's lesson, which is Pandas, NumPy, Matplotlib, and Seaborn. The last two are going to be used for visualization purposes. And before we start, we're also going to need to load our dataset. So we're using the pd.readcsv, and we're just calling the file name, which is studenthabitsperformance.csv, and it's located here. And for this to work, your CSV file has to be in the same folder and directory as your notebook. So df.head is going to print the first 5 rows of the dataset. If you want to get the first 10 rows, you simply put 10 in the brackets and you get the first 10 rows. If you want to get the last 10 rows, you swap out the head for a tail and you get the last 10 rows. So you'll notice that there is a column here, mental health rating. And as you can tell from the title, this is a rating. So this is, while it's a numerical column, as in it contains numerical values as integers, but it should be a factor because it is representing something else. It is representing how good or how bad the student's mental health is by a rating from 1 to 10. So we're going to be coding this mental health rating column as a category. And you can do that by using .astype category. And if you use df.shape, you're going to get the number of rows and number of columns in your dataset in this order. So we've got 1,000 rows and 16 columns in our dataset. If you want to get to know the different data types of your columns, you simply use df.dtypes, and that's going to give you all of your columns and their corresponding data types. So when you have an object, that means that it's a categorical column. And when you have int64 or float64, that is a numerical column. So student ID is a categorical column, whereas age is a numerical column. And the different columns that we have are student ID, age, gender, study hours per day, social media hours, Netflix hours, part-time job, attendance percentage, sleep hours, diet quality, exercise frequency, parental education level, internet quality, mental health rating, extracurricular participation, and exam score. So we can also check the number of missing values in our dataset, the total number in each column, by using df.isNull.sum. So you can see that there's just a whole bunch of zeros because in our dataset, there are absolutely no missing values. So it is a complete dataset, which is great, but also not something that you're likely to be lucky enough to encounter often in the real world. You can also get the summary statistics of all of the numerical columns in our dataset by df.describe. So this is going to give you the mean, the standard deviation, the minimum, the first, second, and third quartiles, and the maximum value of each of the columns. So we know that the average age of students in this data set is 20.49 years, the youngest student is 17 years, and the oldest student is 24 years. Similarly, with study hours per day, the average student, or the number of hours studied on average by all the students in this data set is 3.5 hours, whereas the most hours studied per day by any student in this data set is 8.3 hours. You can get similar statistics for all the other numerical columns like social media hours, Netflix hours, attendance percentage, sleep hours, exercise frequency, and exam score. We can also see that the average exam score was 69.6, and the lower quartile is 58.475. So that means that 25% of the students scored below 58.475, or 58.4, and 50% of the students scored below 70.5, and 75% of the students scored below 81.3. The minimum exam score was 18.4, and the maximum was 100. We can also extract the categorical and numerical features in our data set by using this function here. So we go df.select dtype. So this is going to select a particular data type. And what we're saying is to just include the object or category data types, or columns that have either object or category as their data types. And then we are changing all of these columns so that they're listed in a list. Similarly, we're doing the same thing for numerical features. We're only including columns with the data types D types, int64 or float64. And we are assigning them to these variables, categorical features and numerical features, and we're just going to be printing them out. So the categorical features in our dataset are student ID, gender, part-time job, diet quality, parental education level, internet quality, mental health rating, and extracurricular participation. The numerical features are age, study hours per day, social media hours, Netflix hours, attendance percentage, sleep hours, exercise frequency, and exam score. Another cool thing that you can get for categorical features is value counts. So this is going to be giving you each level of a categorical column and its corresponding value counts. So the value counts are the number of rows that correspond to that particular level of that categorical column. So if you look at the column gender, there are 3 levels in this column: female, male, and other. And we know that there are 481 rows that have female listed under the gender column. Or in simpler terms, there are 481 female students in our data set. Similarly, there are 477 male students and 42 students who identify as other. For a part-time job column, you see similarly 785 students do not have a part-time job, whereas 215 do. You'll also notice that all of the value counts are listed in order of most to least frequent, which is always going to be the case. And let's move on to some histograms for the numerical features to look at their distributions. And let's take a closer look at the code that we used to create these histograms. Numerical features is referencing the list that we created earlier, where we split all of the dataset's columns into categorical and numerical features. The .hist function is used to create histograms of all of those columns, all of the columns inside the list of numerical features. Bins equals 20 tells the histogram to divide the data range into 20 bins of equal width. So each of the bars here in the histograms, each of these bins, they represent the frequency of data points that fall within the bin range that we've specified over here. Fig size equals 12.8 is setting the size of the figure. So this is the entire figure. So we're saying that we want the entire figure to be 12 inches wide and 8 inches tall. The plt.subtitle, that's just creating a title for our visualization. So adds that distributions of numerical features title as an overarching title to the entire distribution. And plt.tight layout is adjusting the spacing to make sure that the plots aren't overlapping because we're creating multiple plots here. Plt.show displays the entire figure, and anytime you're creating a visualization, you need to have plt.show at the end. So we can see that study hours per day is roughly symmetrical and bell-shaped, indicating that it is normally distributed. We can also see something similar for the sleep hours column. And for social media hours, you can see a slight right tail here. So the right tail is longer than the left tail, which is obvious because you can't have negative social media hours. So this right tail here means that this is a skewed distribution. It is positively skewed or right skewed. And you can see that with attendance, you can see the same thing with Netflix hours as well, where you've got a bit of a right tail here. And with attendance percentage, you've got the opposite. You've got a left tailed. So this is a negatively skewed distribution, as is exam score. And this also makes sense because you can't have an attendance percentage that is higher than 100, the same way you can't have an exam score that is higher than 100, and the same way you can't have Netflix hours that is less than 0. Let's look at a correlation heat map of our numerical features. So this is going to be listing the correlation between all of our numerical features. The first thing you're likely to notice is that all of the diagonal squares in this correlation matrix are red with a correlation coefficient of 1.00. This means that this particular square represents a perfect correlation, which is what you'd expect because the age column is going to be perfectly correlated with itself, which is highlighted by or indicated by the 1.00 correlation coefficient, which indicates a perfect correlation. Similarly, study hours per day is also perfectly correlated with itself. Social media hours is again perfectly correlated with itself. Netflix hours is perfectly correlated with itself, and so on. But the column that we're going to be most interested in here is this last column here, because we're looking at the relationship of all of these variables with the student's exam score. So these are all of the students' either demographic information or their habits. So these would be what you'd call the independent variables. So these are the factors that we think could influence the exam score. And because the exam score is a variable that is being influenced, it is called the dependent variable. So we're just interested in this final row here. And you can see that study hours per day is pretty highly correlated with exam score with a correlation coefficient of 0.83. And this high correlation is also indicated by an orange square. And you can see over here in this key area that the higher the correlation, the more orange or red the box is going to be. So for those that are not acquainted with correlation coefficients, this is just a brief interpretation. Something to help you interpret those correlation coefficients. So when the correlation coefficient is between 0.8 and 10 and 1, this is considered a very strong relationship. When the correlation coefficient is between 0.6 and 0.8, it's considered a strong relationship. When the correlation coefficient is between 0.4 and 0.6, it's considered a moderate relationship. And when the correlation coefficient is between 0.2 and 0.4, it's considered a weak relationship. A 0.0 to 0.2 is considered a very weak or no correlation. And you'll notice here that apart from study hours per day, all of the other columns are below 0.2. So all of the other columns have a very weak correlation or no correlation with exam score. So we're going to be exploring only a couple of these columns here based on their correlation coefficients. So we're going to be looking at study hours per day, social media hours, and Netflix hours. And we're also going to be looking at one of the categorical columns that I think might be interesting, which is the mental health rating. So let's look at a scatter plot of study hours per day and exam score. So you can see here that if you draw a line right through the middle of this pattern, it is going to be a straight line. as in it can be described by the equation y equals mx plus c, the linear equation. You can also see that there seems to be a relationship here. The more hours per day a student studies, the higher their exam score seems to be. So this is what we call a positive linear relationship. So this is a strong relationship, as you can tell by the clear pattern that you can see in this visualization, and also by the correlation coefficient of 0.83, that this is a strong relationship between the number of hours the students studied per day and their corresponding exam scores. There is a clear linear relationship that can be observed in the scatter plot, and the nature of this relationship is positive, as in the more hours a student studies per day, the higher their exam scores are likely to be. And there's a clear upward trend. As study hours increase, the exam scores tend to increase as well. And this pattern indicates that study time has a strong influence on their academic performance. At around 6+ hours a day, many students reach near 100% on their exam scores. So this is around the 6+ hours a day mark. So when you're going beyond this, most of the students are above 70 and 80, and as you get slightly higher, like around, say, like just short of maybe 7 hours, they're already reaching the 90 mark. And most of the students here are also around the 100% mark as well. And you can see that there are a lot fewer students who study more than 6 hours per day as well, with most of the students studying between about 2 to 6 hours per day. But once they reach over 6 hours, a lot of them are reaching that 100%. And this suggests that maybe after a certain point in the number of hours that you study per day, there isn't really that much of an improvement in your exam score, because again, this is a left-skewed distribution. You can't get higher than 100. And most of the students, after spending 6+ hours a day studying, do reach that highest point of 100%. So beyond a certain point, more studying doesn't drastically boost their scores further. And you also notice that there are two different colored points here, data points. So the blue points correspond to students without a part-time job, whereas the orange points correspond to students that do have a part-time job. So each of these data points represents a student. So you can see that there's no clear clustering, there's no explicit segregation of these two groups, which suggests that having a part-time job or not does not significantly affect their exam scores or the number of hours that they're able to study per day. So even if a student does have a part-time job, so long as they're putting in the hours, they're going to be seeing pretty good results in their exam scores. So students with part-time jobs are generally well distributed and perform similarly to those without part-time jobs, because again, there's no clear segregation or clustering that we can see in the visualization. And this suggests that having a part-time job doesn't necessarily harm performance, especially if the study time is maintained. So students who study less than 2 hours per day tend to have more varied and often lower scores. So you'll see that all of these students here, the points are more tightly packed, but when you get to below 2 hours per day, the points are a lot more further apart. They're more spread out. So there's a lot more variation in the data points below 2 hours of study per day. So they tend to have more varied and often lower scores as well. So this indicates that low study hours negatively affect their academic performance, which is something that you'd expect. So let's look at a scatter plot of social media hours and exam score. So you can see that the students, which is the data points, are scattered across the graph pretty randomly. So this means that there isn't a very strong relationship, if there's a relationship at all, between social media usage and the students' exam scores. And again, there is no clear segregation or clustering between the two differently colored data points. So that having whether or not a student has a part-time job doesn't seem to affect either their exam scores or the number of hours they spend on social media. So let's summarize this. Students are scattered across the graph pretty randomly. There isn't a very strong relationship between social media usage and exam scores at a glance. Whether or not students have a part-time job doesn't seem to drastically change the relationship between social media use and academic performance. Both groups are similarly spread out, like we said before, no clear segregation. And a lot of students spend between 0 to 3 hours on social media daily. And you can see that here with when you draw a vertical line right at that 3 mark, you can see that most of the data points fall to the left of it, with fewer on the right of it. So most students do spend between 0 to 3 hours on social media per day. And exam scores are spread out across the board in this range and also beyond this range. You can see that there's no clear pattern like we identified with the study hours that we can see here. There's no line that can be drawn here that can best represent the data like that linear line that we drew with the study hours per day graph. So there might be a slight trend suggesting a higher social media usage is associated with slightly lower scores. So you can see that when you have students using social media for over 6 and 7 hours per day, they're actually getting scores that are below 50. And you'd notice that if you remember before, if you recall, we saw that the mean exam score was 69. So they're actually scoring below average if they're spending a significant amount of time on social media. But this is a very weak relationship visually, if it is a relationship at all, and also based on the correlation coefficient, which is only a negative 0.17. And that's something that I also meant to mention. If the correlation coefficient is in the negative range, then it is a negative relationship. If it is in the positive range, it is a positive relationship. So when you have 0.83 for study hours per day and exam score, that is a strong positive relationship. When you have negative 0.17 for social media hours and Netflix hours, that is a very weak negative correlation. So let's move on to a scatter plot of Netflix hours and exam scores. So you notice that this graph is very similar to the graph that we saw above. There's no clear segregation between the blue and orange points. So there's no clear segregation between students that do and don't have a part-time job. There also is no obvious pattern or relationship that can be seen visually between the number of hours spent on Netflix and the students' exam scores, but you can see that as the number of Netflix hours increases, as it gets over 4.5 maybe, the students' scores tend to get lower. But again, at the 4-hour mark, you still have students scoring pretty high over here. So there doesn't seem to be much of a relationship between the hours of time, the number of hours a student spends on Netflix and their exam score. And you also have a student here who spent over 5 hours daily on Netflix, and they scored above 70, close to 80. So the relationship is very weak again. So this pattern looks very similar to the social media hours graph that we saw before, and there's a very weak or no clear correlation between the time spent watching Netflix and their exam scores. So students watching between 0 to 2 hours of Netflix daily seem to have a wide range of scores. So there are students who are scoring both very low, like students who only spend an hour on Netflix, but they're still scoring below 30. And you've also got students that are scoring at 100%. So there's a very, very high variation here. And higher Netflix hours, as we talked about, like above that 3-hour mark, seems to be associated with slightly lower exam scores, but again, the relationship is very weak and it's not obvious. And again, like we said, no segregation, so having a part-time job doesn't seem to be visibly affecting this relationship either. So let's look at exercise frequency as well while we're at it. So you'll notice that this scatter plot looks slightly different. There isn't going to be anything in the middle of these two because, again, you can't exercise half a time a week. So a student either exercises 0 times a week, 1 time a week, twice a week, thrice a week, and so on. So you'll notice that, again, there is a very even distribution of students with and without part-time jobs in each of the exercise frequency groups, and there also seems to be a wide range of exam scores at each of the exercise frequency levels. So exercise frequency seems to be also of very weak correlation with academic performance. So to summarize this, exam scores are widely spread across all exercise frequencies. There's no clear pattern like more exercises equals better grades. And students who exercise 3 to 5 times a week don't necessarily score higher than those who exercise, say, 0 times a week. And whether a student has a part-time job or not doesn't drastically change the spread of exam scores. And there's also a very even, or like what appears to be a very even distribution of students with and without part-time jobs in each of the exercise frequencies as well. So there are students with part-time jobs that are exercising 6 times a week, although I suppose when you're looking at 6 times a week, there does seem to be fewer students with part-time jobs exercising 6 times a week and more students without part-time jobs exercising 6 times a week, which is probably something that you'd expect. There's also a very dense clustering of scores around the 50 to 90 mark across all exercise levels. So fewer students seem to be scoring below that 50 mark here. A lot of the data points are focused and concentrated around that 50 to 90 mark. Exercise frequency and having a part-time job do not seem to have a strong, clear relationship with exam performance based on the scatter plot and based on their correlation coefficient, which was below even 0.17. But it is a positive correlation. So it's a positive relationship, but it is very weak indeed. So exercise frequency and part-time work don't show an obvious correlation to exam scores, neither do Netflix hours or social media hours. So the only thing so far that we've seen to have a strong correlation with exam score is study hours per day, and it was a positive correlation. Let's look at a box plot of mental health rating and exam score. So there are 10 different ratings that you could get in on your mental health. Between 1 to 10, and this graph is called a side-by-side box plot. So you'll notice that you have this line over here. So that is the top of the range, that's the maximum value, and this line here is the minimum, that is the bottom of the range. The line in the middle of the boxes is the median. This line over here is the first quartile, which means that 25% of the data points fall below this line here. And you can see that 50% of the data points fall below this point here, which makes it the median. 75% of the data points fall below this point here. And anything that exists outside this range are outliers. So this point here and this point here are outliers. And this is this is also called a box and whisker graph. So this is a box, and these lines that stretch out to these sides are the whiskers. Okay, so you can notice that the median seems to go up as you move up in rating for the mental health. So students with higher mental health ratings, as in ratings that are closer to 10, seem to have a higher median exam score, which again is something that you'd expect. There are some outliers, as we pointed out here, in the lower mental health ratings, namely mental health rating of 2. We noticed an outlier here. And surprisingly, there is a student who had a mental health rating of 2 who still managed to score 100%. So this suggests that some students still perform very well, even if their mental health is rated lower. And ratings from 7 to 10 seem to have slightly higher median scores than the lower mental health ratings. So you'll notice here that the median line for ratings from 7, 8, 9, and 10 actually fall above the median line of the lower ratings like 1, 2, and 3. So there's a discrepancy in their median exam scores based on their mental health. So better mental health, unsurprisingly, seems to be associated with slightly better academic performance, but there's still a lot of variability, and the relationship doesn't appear to be very strong based on this visualization. We can also look at we can also use the group by function to get the mean score, not the median, but the mean exam score of the students that belong to each of the 10 mental health rating categories. So you'll notice that it does indeed increase, their exam scores does indeed increase as their mental health rating increases. So that is going to be the end of today's video. I hope it was helpful, and thank you for watching.